Hi guys, we're gonna continue with our discussion on springs, and in this topic or lecture we are going to cover the buckling of springs and the vibration or natural frequency of a typical spring, and finally we are going to be doing an example that we will go through right now. A spring buckling will occur if the spring length is greater than its critical value, which is 2.63 times d over alpha. So if the free length of the spring is lower than that, then the spring will not buckle, which sort of makes sense, right? If you have a spring, so the longer the spring, right, the more chance that the spring will basically buckle, and by buckle it will basically do this, right? And you don't want that to happen, for example, in your application. To ensure that the spring will not buckle, its length would have to be lower than this value. To get this value, so we have alpha and we have d, and we also have L0, and L0 is going to be the free length of the spring. So this is pretty basic, but if you want to get into more details on that, we can basically get the critical deflection. So even if the spring is tall, right, this condition here will guarantee that the spring will never buckle, right? But if you still would like to work with a long spring and you want to see, I'm going to draw it here. So let's say I have a very long spring, right? It is actually possible that if I deflect that spring a little bit, right, it won't deflect, right? So this is called YCR, which is a critical deflection that I could give on a spring before it basically buckles. And this critical value is given to you by this equation here, and you should, while you are going with me, basically, you should definitely take notes because, if you can't read that. So here you have the critical length is L0. L0 is the free length of the spring, which we showed in my previous lecture how to get that based on the number of active coils, etc. multiplied by these two constants, C1 prime and C2 prime. So I have C1 prime 1 minus C2 prime over lambda squared, all square root of this. And in that critical length, you have two variables. One variable is C1 prime, the other variable, or three variables, C1 prime, C2 prime, and then lambda. Lambda is given to you as the slenderness ratio, which is essentially the ratio of this distance divided by that distance, right? Basically that d over or L0 over d, right? And the larger this value, then the spring will will probably more buckle, right? So you want d to increase and then L0 to decrease, right? So increasing the diameter and reducing the length will obviously reduce the likelihood of the spring buckling. All right, so we got C1 prime, C2 prime, and then the slenderness ratio is given to you directly here. What remains is the constraints of that spring. So depending on how that spring is, if that end is free and then that end is free, then you have to use these conditions that we have. So that would be a free length essentially is a pivoted length. So that point is pivoted about a hinge. And so we have here all these conditions that you have. Obviously, you never have like, two free situations like a spring like that, because that spring itself will not set. So we have spring supported between flat parallel surfaces, essentially fixed ends. So they are fixed and they are parallel. And you would see here, this is the greatest when one end is clamped and the other end is free, right? So based on the mounting situation of the spring, you are going to update that value alpha, and alpha is going to be embedded into this equation when you are ensuring that the spring will never buckle. All right, and alpha will also goes here, right? In the slenderness ratio, you have to use alpha, and also this global equation that makes sure that the spring will never buckle. Okay, so this is it for the buckling of springs. Again, check these tables again here, the different mounting conditions of springs. And lastly, regarding springs, is what I would like to go over is the natural frequency of a spring. So here you don't really need to go over the equations that or the wave equation of a spring, because you have some density that basically fluctuate. So the coil itself it results in natural frequencies, and then inside the spring some coils will actually vibrate as well, so the spring itself will have mood shapes. We won't be going over that, but what we will do is we are going to go over the natural frequency, and then primarily the first natural frequency of the spring, and that is given to you as this function, right, or this equation, 1 over 2 square root of kg over w, where w is the weight of the spring. We can get the weight of the spring from the volume of the spring, which is pi d square, which is area of the wire, right, multiplying this by the mean coil diameter by Na by the density, so multiplying the volume times the density, that would give you the weight. And pi d square over 4 is what will give you the basically the area, right, pi d square over 4, because the area of a circle is pi r square, right, so that the first portion is the area of the wire. So this is the natural frequency of a spring if I ask you for it, and this is the natural frequency if the spring is held between two flat and then parallel plates. So in that situation, then this is going to be our natural frequency, but in the case of one end is free and the other is against a flat plate, like in that case you have one plate, in that case, and the natural frequency is equal to 1 over 4. Right, so this is the first natural frequency in the case of one end free and the other end is clamped on a parallel plate. Overall, regarding the overall design guidelines of springs, if you are designing or trying to make your own spring, obviously the wire would should be commercially available, and here we said they have to be music wires, right? This is what people typically use. The stresses of the solid length of the spring should be less than the torsional yield strength. What I mean by that is, if you have a spring and if you the spring is going to be obviously in the free length, and if you close the spring solid, so basically if all the coils now you fully basically press that spring here, your shear stress would have to be less than your yield shear stress, right? So that makes sure that even if you fully clamp the spring will never be yielding. So when you release it, it will come back to its original length. And that is a main guideline in springs. And this is what happens in the case of usually like, car suspensions. Sometimes you would see that the suspension will essentially bottom down, right? And it will basically retract and nothing will happen, right? Why? Because the spring was designed in a way where the maximum shear stress in the wire will be always lower than the yield. The maximum operating force has to be limited to 7/8 of your maximum force, and the maximum force is the force that will cause the spring to yield. And by the way, the failure of springs will always be caused by yielding. It's never possible that you fully that you exceed the ultimate tensile strength of a spring, because the only load that we have in a spring is shearing. And it is preferred that the range of the spring index to be between 4 and then 12, and we said the index was equal to d over small d, right? You can look that up also in the previous equations that I provided for you guys. All right, so now we can. Okay, I would like now to do a brief review on the springs or the stresses in the springs before I do an example. And let's say this is portion of that wire which is like helix, like going up, and we said here you are going to have this force, the shear force, and then you're also going to have a torque applied on that, and that torque was equal to Fd over 2, where d is the mean coil diameter, and based on these two we're going to have the maximum stresses on here. So we said the shear over here is going to be equal to how much? Kb multiplied by 8 Fd, divide that by pi d cube. So this is a very important equation that you should memorize, or you should know on the second exam or the final. This is the shear at that point, and we said the maximum or the maximum shear in yield is going to be equal to 0.45 SUT, and this is in the case of music wires, right? So when you want to calculate the force at yielding, you're going to replace this shear by this value, right? And what was SUT equal to? SUT was equal to how much? A over dm, and we can look up these the m and then the a. We can look them lookup table, right? So you look up a and then m, and then d is going to be this diameter, right? So d was equal to the wire diameter. All right, and finally, what we also introduced is the stiffness of the spring, and then we said the stiffness of the spring, K, was equal to how much? F over deflection, and that was equal to d4g, divide that by 8 d cubed times NA. All right, so we have the shear value based on a given force, given geometry, and we can calculate that. We can mainly calculate, for example, the safety factor for yielding by dividing this value divided by that, and we use SUT to be able to find this SSY. SSY is essentially, we referred to this before as tau y, right? That would be the yield, the maximum yield stress of the material. And again, we got this guy from the energy equation, and then differentiating the force or differentiating the energy relative to the force will give you the deflection. All right, so now we can work on this example, and this example is in your notes. What we have is a helical compression spring is made of number 16 music wire with outside diameter to be 7/16, and the ends are squared, and there are 12 and half total turns. So total turns is NT, right? Is not NA. Estimate the following parameters. We have to estimate the yield strength, the yield force, the spring rate, deflection of the spring at yield, solid length of the spring, and then the free length of the spring. So let's go at them one after another. Okay, so we're gonna begin by finding the yield strength, right? So essentially it is torsional yield torsional yield strength, and we already just described that, so that would be SSY, and that is equal to 0.45 SUT. We don't know what SUT is, so we have to look it up based on this equation, AD to the power M. So from table 828 in my notes, essentially you can find based on this wire diameter. So number 16 will give you diameter equal to 0.037 inches, and from table 10.4 we can get A and also M. So A is equal to 201 KSI inch to the power M, and M was equal to 0.145 also from that table. Okay, so now I can find my ultimate strength. It's going to be equal to A d to the power M. I already calculated A and then M and then also D. So this guy would be 201 divided by 0.37 to the power 0.145, and this is going to be equal to 324 KSI. So now we just calculated the ultimate strength of that, and to calculate the torsional yield strength, SSY or tau y, which is again SSY, it will be equal to 0.45 times SUT 324, and that is equal to 146 KSI. Okay, so when you have a spring based on the wire values, you can directly get the yield stress of the wire. The second question on here, we had to find the yield force. As I said earlier, so this is a spring. The maximum shear is going to occur here, and we just mentioned that that shear is equal to KB8 FD, divide that by pi d cube, right? The force that causes yielding, they are linearly related, so I can simply solve for Fy, right? So Fy is going to be equal to pi d cube tau I divided by KB 8 times d. We need to know KB. KB was already given to us. This is a factor that essentially takes care of the curvature of the spring because we were using the average shear stress. So that will be 4C plus 2 divided by 4C minus 3. And C was a spring index, so C was equal to D over D. And in our case, it will be equal to 0.4 divided by 0.037. C is going to be equal to 10.8. So once you get C, you can get KB to be equal to 1.24, and then I encourage you guys, while you are doing that, you can also check out your lecture notes as well, and mainly the presentation. So now we have KB, we can come back and then find Fy. Fy in our case is going to be equal to pi d cube SSY divided by KB 8 times d, which is equal to pi 0.37 cube 146 times 10 to the 3, right, which is what we just solved for in the previous part, and that is divided by 8 times 1.124, which is K, multiplied by 0.4, which is the mean coil diameter. All right, doing that, you will see that Fy is equal to 6.46 pounds. In our case, in the case of this example, what they gave you is they gave you, let's say this is, you know, like a cross section in a spring, right? And then these are the cross sections. In that problem, essentially what they gave us is this outside diameter, right? And then this is the mean coil diameter. And we know this here is small d. So d outer is equal to, if I want to get d, the mean coil diameter is going to be the outer minus, right, d over 2, and then d over 2 minus d, right? And I think it should be very easy for all of you. Okay, so we got the two things that we need, and then these are basically really the common stuff that people typically use when they are working with springs. Okay, so this is, you know, standard stuff that you are learning here. The spring rate, so we already said the spring rate was equal to how much? This is the equation for the spring rate, d4 g divided by 8 d cubed times n, right? So we know our d, right? And we need to know the modulus of elasticity, right? And we need to know the number of active coils. All right, from table 10.5 you can find G for various types of wires, right? And in this case, G is going to be equal to 11.85 m psi, right? Mega psi, or 10 to the 6. Okay, we need to know the number of active coils, but in the problem, basically, they gave you 12.5 total turns, right? So we have our NT was equal to 12.5 total turns. So total turns doesn't necessarily, so in the case of the spring, right, total turns doesn't mean number of active coils. Why? Because if the spring is closed and grounded, right, then you have some portion of this is not basically taking any load, right? Because you already squared this and it is sitting on there. So this portion, right, it would all be subject to the same, it wouldn't basically be experiencing the same load that you are getting here and here and there and there, right? Especially if the spring is fully closed, like basically you have one more turn here that is simply doing nothing but maintaining the length of the spring. So only a tiny portion of that last coil is used to take any load. So we have NT. How do we get NA? What you have to do here is, I think you should know by now, we have a table, right, that we were using, and I'm going to pull up that table right now. Yes, this is a table that we have, and in the example that we had the spring which was square and closed, right? In that case, you wanna come to here. This is what I meant. The ends are squared, so here you're gonna go and squared. So in the case of squared, it doesn't really matter if they are squared or closed or squared and ground. Why? Because total number of coils are equal to an A plus 2 or an A plus 2. So essentially, when you are closing the spring, you are two coils are not being used, because one coil is being used to close one end and the other coil is being used to close the other end, and that is why it's going to be an A plus 2. So in that case, we know the total is going to be equal to NA plus 2, or NA is going to be equal to NT minus 2, right? So if you have in total 12.5 turns, so you have to remove one end from here and then one end from here. So the actual number of active coils is going to be equal to 12.5 minus 2, which is 10.5. So now you have this. Now you can take this number of active coils back over here, so you can get the stiffness of the spring. And in that case, your K is going to be equal to how much? K is going to be equal to 0.037 to the power 4, which is, this is the wire diameter, multiplied by 11.85 times 10 to the 6, and the whole thing is divided by 8 multiplied by 0.4 to the power 3 times 10.5, which is going to be equal to 4.13 pounds per inch. So this is how you calculate the stiffness of the spring. Next, we would like to calculate the deflection of the spring at yield. By that, this is a spring, right? And then we have one end here, and then one end is like that. And let's say this is fixed. We would like to find the deflection before that spring yielded. So we have already calculated Fy, right? We said that Fy was equal to pi d cubed times the y divided by kb times 8 times d. We calculated this force that would cause one of them to, or the coils on the inner fiber to yield, and we just calculated the stiffness, and we know F is equal to K times X. So at yielding, we can find the deflection at yielding, right? Because the more the force, the more the deflection. So I can essentially find the deflection at this force. So if I apply that force, I know the spring is going to move a little bit and then it's going to stop, right? Because the force applied by the spring is going to be equal to the force which I'm applying. So the deflection at yielding is going to be equal to Fy over K, and we have calculated both of them. In that case, it would be 6.46 divided that by 4.13, and this would be equal to 1.56 inches. So 1.56 inches is how much that spring will retract. So ideally, what you should do, if you are making your own spring, you should make that distance, right, to be less than, so essentially you would want your spring to, you want the solid length to be somewhere here, right? So the spring will essentially close, right? And in that case, you would be able to no longer close the spring, right, if it exceeds the solid length of the spring, right? This is what you want to do so that you definitely prevent yielding, because the coil will be basically sitting on each other. Next, we would like to find the solid length of the spring. And how do you find the solid length of the spring? Is you have to again look up the table that we have. So the solid length, or some people call it LS, which is what they are calling it here. So LS is going to be equal to how much? In the case of our spring, it could be either D times NT plus 1 or D times NT. But in our example, they don't really say if it is squared and ground. They tell you simply it is squared or closed, right? So in that case, on the exam, I will tell you if it's ground or not, right? If it's squared simply, then it's not ground, then you have to use this. In that case, the solid length of the spring is D. D is again the wire diameter, right? So simply if you are closing the spring, obviously, so this is, like one wire, and then this is the other one, and then this is the other coil, and then this is the other coil, and they are all touching essentially. So the solid length is going to be simply the number of tiny diameters that are there, and in that case, in the case of that spring, it will be D multiplied by NT plus 1. All right. So that would be the total length of the spring, because obviously when you close one wire, right, it's going to add up to the length of the spring. That is why you still have plus 1. So here, just apply the equation, and it will be D was equal to 0.037, right? This is a wire diameter, multiplied by NT, which is 12.5 plus 1. And if you do this, you will actually get 0.5 inches. So this is your length. Last thing is to find the free length of the spring, and well, like I mentioned earlier, the solid length of the spring is going to be, when it is fully tight, and we also find how much distance basically is yield distance, right? And this is a distance that we got from xy, right, was equal to Fy over K, right? And that was our LS. So essentially the free length of the spring would have to be this one, or less than that, right? If the free length of the spring is less than that, then essentially you make sure that xy can only be at most xy and then lower, right? So L0 would basically have to be less than LS plus xy. So this is a general convention, but it doesn't have to be that way, right? You can make it, and then you can have some other constraints other than solid length of the spring, right? But ultimately you would want to have this to make sure that even if you compress xy, right, starting from the free length of the spring, right? Xy is always from the free length of the spring where you have no forces, right? So starting from the free length, you would want this xy to be, or x, this is x, right? So the most deflection that you can create is to be equal to xy, so that xy plus ls is actually equal to L0.